In this video, we're going to take a look at dividing polynomials, and specifically dividing polynomials, which will lead us to finding zeros of polynomial functions. So let's start out with some terminology. If I have two polynomials divided, f of x divided by g of x equaling q of x plus remainder r of x, we say that the dividend is f of x, the divisor is g of x, the quotient is q of x, sometimes that's uppercase q, sometimes that's lowercase q, and the remainder we'll call r of x. So those are the terms we're going to use for each. Dividend divided by divisor equals quotient plus remainder. Now, the first way you probably learned how to divide polynomials is through long division. We'll go over that right now, and then we'll add another method of division in the later half of this video. Long division is a process where we repeatedly ask what needs to multiply first term of the divisor to match the lead term of the remaining dividend. Once I figure out what that is, then I can multiply the entire divisor by that term and then subtract whatever I get from the remaining dividend. So it's best just to do an example, I think. Let's divide x to the third plus 5x squared minus 8x minus 10 by the polynomial x squared plus 3x minus 4. All right, so let's go ahead and do that. Here we have x to the third plus 5x squared minus 8x minus 10 divided by x squared plus 3x minus 4. I put the dividend underneath a sign, just usually is just a vertical line and then horizontal line over that dividend. And then the divisor I put out front. That's usually the notation that we use. And then I ask, what do I need to multiply x squared by to get an x to the third? Well, the answer to that is an x. So I write it above. I tend to write it all in alignment. So I write it above the minus 8x just because all of that is x to the first. Once I do that, then what I do is I go to right underneath my dividend and I multiply x by x squared plus 3x minus 4. That's going to give me an x to the third plus 3x squared minus 4x. And I try to, as much as I can, align that underneath the correct terms, so the like terms. Now what I'm going to do is I'm going to subtract. And in particular, I'm going to subtract this entire polynomial. Maybe that doesn't look very well, but so I'm subtracting that entire polynomial. Again, if I were a little bit better with this, I could have aligned it a little nicer. Once I've subtracted this entire polynomial, that's going to give me, well, x to the third minus x to the third are canceling each other out. That's why I chose x here. 5x squared, then we have a minus 3x squared. So I get a positive 2x squared when I subtract those. 8x minus a negative 4x becomes a minus 4x. And then the minus 10 doesn't have any like terms, so it just falls down. You'll often see a line when people do subtracting at this stage, just like that. Now we're ready to do this again. We say, I have as my leading term here of my remaining polynomial 2x squared. What do I need to multiply by x squared to get 2x squared? The answer to that is a positive 2. So I write down plus 2, and then I multiply that positive 2 by x squared, 3x, and minus 4. When I do that, I'm going to end up with a 2x squared plus 6x minus 8. And then once again, I'm going to subtract that. Again, usually we write a line underneath, and then I put parentheses around the entire polynomial, and I'm subtracting that entire polynomial. So we subtract that, and what that yields, 2x squared minus 2x squared gives me 0x squareds. Minus 4x minus 6x gives me a minus 10x. Minus 10, and then this is going to be a plus 8. So minus 10 plus 8 gives me a minus 2. Now, there's no whole numbers or whole number exponents that I can multiply now. Variables with whole number exponents that I can multiply an x squared to get a negative 10x. So since this polynomial is of lower degree than my divisor, I can stop. And this tells me that when we do the division, we are going to get x plus 2. And there's a couple of ways you can write this. You can say plus remainder of negative 10x minus 2. Another way you can write that is x plus 2 plus, and then as a fraction, you say, I'm left with negative 10x minus 2 over my divisor of x squared plus 3x minus 4. So that's another way you can write that. So either remainder negative 10x minus 2, or the remainder is actually the part which you can't divide, that you haven't divided by that divisor yet. So either way is all right. But that's the idea of long division. Long division at each step. I know I subtracted this, but at each step, we ask, how do I match this leading term? And then I take and subtract whatever I have here. I do that until I get a polynomial of lower degree than my divisor. And once I hit that, then I can stop. That polynomial of lower degree is my remainder. Let's do another example, but this time I'm going to let my divisor be x minus 2. That's a linear divisor, and specifically, it's a linear divisor with a 1 out front. We'll use long division in this case. All right, let's try this. So, what do I need to multiply by x to get x to the third? The thing I need to multiply by x to get x to the third is an x squared. So I write that down. And again, usually I align it with the other x squared terms. So I multiply x squared times x minus 2. That's going to give me an x to the third minus 2x squared. And then I put that in parentheses and subtract. Once I do that, technically a lot of times people will underline this. Once I do that, let me kind of move this back a little bit. Now we're good. All right. So once I get to that stage, excuse me, I end up with a 7x squared. That's 5x squared and then plus 2x squared. Be careful about that. Minus a negative gives me a plus 2x squared. So 7x squared minus 8x minus 10. And then I do the same process. I ask myself, what do I need to multiply by x to get 7x squared? The answer is a plus 7x. If I do that, I get 7x squared minus 14x, and then I'll subtract the whole thing. Again, I'll just underline that to show you what's going on. When I subtract that, what I end up with, 7x squared minus 7x squared gives me 0. 8x minus a negative 14x, that's 8x plus 14x. That gives me 6x minus 10. And then I go through that process again. I say, what do I need to multiply x by to get a 6x? The answer there is a 6. 6 times x is 6x. 6 times minus 2 is minus 12. That is going to produce 6x minus 12. And then I subtract that whole thing. When I subtract that whole thing, again, usually I'll put a line underneath of it just so that I can see what I'm doing. Negative 10 minus a negative 12, that's like negative 10 plus 12. I get a positive 2 as my remainder. Now I want to point something out. Because I was dealing with a linear expression here, as my divisor, my remainder is just a numerical value. It's not a polynomial with multiple terms. It's just a constant. And so what this means is that this fraction is actually equal to x squared plus 7x plus 6 plus remainder of 2. Sometimes people would say with remainder of 2 or plus remainder of 2 or something like that. You could have also, like we did previously, say that's actually equal to x squared plus 7x plus 6, and then add the fraction 2 over x minus 2. That's another way to write the answer. Remainder 2 means we haven't yet divided that 2 by my divisor of x minus 2. So either one of these is an appropriate answer. Let's do one more example of long division. This is example 3. If you want, push pause on this video and try it on your own. If you don't do that, or if you do that, I will show you how it's done in a couple of seconds. All right, so I'm going to do this. First thing I'm going to do is say, what do I multiply x by to get x to the fourth? The clear answer to that is x to the third. So then what I do is I multiply x to the third by x plus 3. What that's going to give me is an x to the fourth plus 3x to the third. I subtract that polynomial off. Whoops. And once I do that, the remaining polynomial I get, my dividend minus this, is going to be minus 2x to the third minus 3x squared plus 4x minus 5. Then I go through my process. What do I need to multiply x by to get negative 2x to the third? Well, the thing I need to multiply by is going to be a, whoops, I should put it up here first, is going to be a minus 2x squared. Once I multiply by minus 2x squared, I get negative 2x to the third minus 6x squared. And then I put parentheses around all of that and subtract. Once I do my subtraction, I will get a positive 3x squared. That's negative 3x squared plus 6x squared. So that's a positive 3x squared plus 4x minus 5. Then I do the same thing. What do I need to multiply 3x squared by? Or what do I need to multiply x by to get 3x squared? The answer to that is 3x. So I go ahead and multiply that. And I'll subtract as well as I'm doing this. When I multiply that, I will get 3x squared plus 9x. And then I will subtract the whole thing off. And that gives me minus 5x minus 5. Do the same thing. What do I need to multiply x by to get minus 5x? The answer is a negative 5. And so I do that, and I would get, well, I'm going to subtract the polynomial, but the polynomial I get would be negative 5x minus 15. Do that subtraction. And I'd get a positive 10. That positive 10 is my remainder. Again, things aren't lined up perfectly because I'm trying to type these, but you can see what's happening. When I take this fourth degree polynomial and divide it by x plus 3, I end up with this polynomial plus remainder of 10, or plus 10 over x plus 3. Let me go ahead and write that down. So this polynomial is equal to what's on top here, which is x to the third minus 2x squared plus 3x minus 5 plus remainder 10. And again, if you'd like to write that as plus 10 over x plus 3, you could do that as well. So that's what we end up with in these cases. Now, in example 1, dividing by using long division, this is not the only way to actually divide this, but this is a pretty decent way to divide. That is dividing by long division. But in both example 2 and example 3, there's actually a way that in general is quicker than long division. And that is synthetic division. So I'll use synthetic division fairly often, but I want to make sure we're all on the same page. Synthetic division is only going to work when the divisor is of the form x minus a real number. If we have x minus a real number, technically you can do this with complex numbers as well, but in our class we do it with real numbers. So x minus a real number being the divisor is really the only way we'll see. And it's a process that's generally quicker than long division. So it's worthwhile to figure it out. So here's what we usually do. We take the process is this. When we're dividing a polynomial, by x minus r. What we do is we set the r out to the upper left so we don't forget it. And then we write the coefficients of all of the terms of the polynomial, making sure that our terms are in decreasing order and they descend by 1. Then what I do is I drop down the first term. That is a sub n. Then I'll multiply a sub n by r and put it right here. So that'll be r times a sub n. When I do that, I will add these two terms and get something else. And then I'll multiply that thing by r and move it up and to the right. So each step on the bottom, I'll multiply by r and move up and to the right. And each step on top, I'll add the two numbers together and put it down. So every time I go straight down, I'm adding. And every time I'm moving up and to the right, I multiply by r. And if I do that process, then this numerical array will become the coefficients, but of a new polynomial of 1 degree less than my starting polynomial. Let's go ahead and try that process. Let's try it with this. So the usual setup is this. Now we have to be very careful when our denominator is x plus a number. In the synthetic division process, our denominator is written as x minus r. So the r in that case would be a -3 in this situation. That's x minus -3. And then the first step is to put that r here in the left-hand box. Usually I put like a little L around it, reverse L obviously. And then I'll lay out the coefficients of my divisor in descending order. So 1x to the fourth plus 1x to the third minus 3x squared plus 4x minus 5 give me those coefficients. The first step is to drop that 1. I drop that 1 here, and then I multiply the -3 times the 1, and I write it here. That becomes -3 times 1, which is -3. Then I add these two things up. When I add these two things up, I end up with a -2. And then I take -3 times -2. That's going to give me a 6. Adding those things up gives me a 3. 3 times -3 becomes a -9. Add those two up, we get a -5. -5 times -3 gives me a +15. When I add those two things up, I get a 10. And what this says is that when I do this division, I'm going to get 1 as the coefficient of the x to the third term. So we just get x to the third times 1 minus 2x squared plus 3x minus 5 plus a remainder 10, or with remainder of 10. Notice how this took up a lot less room than the process that we had before, the long division process. But it gave me the exact same answer as the long division process. I won't go through why it does that, but you can imagine why it does that. And if you want to look at some other video, you could probably find out why it does that. But for here, when we have denominator, which is x minus r, I can do this synthetic division process. It goes very, very quickly, and I get a really nice answer. Again, if we started with x to the fourth in our divisor, my new quotient is going to start with x to the third, 1 degree less. Hopefully that all makes sense. So that's the synthetic division process. Let's try this next example using synthetic division. This is a 5th degree polynomial divided by x minus 2. This is not something we've done before. But I want you to notice that there's no x to the 4th term. If you want to do this on your own, you can push pause on the video and try it on your own. Otherwise, I will do it in a couple of seconds. Okay, so first things first, it's x minus 2 in our denominator. So we put a 2, that is a positive 2, out here in what I usually refer to as the box. So put a 2 in that box. The coefficient of x to the 5th is a 1. The coefficient of x to the 4th is a 0. And I have to plug that 0 in if I do that. Coefficient of x to the 3rd is -1. Coefficient of x squared is a 2. Coefficient of x is a -4. And my coefficient of my constant or my constant number is a 9. So the key thing there is because we have no x to the 4th term, we put a 0 as a placeholder. That's important if we want to do synthetic division. We have to have that placeholder there. Now the 1 is going to drop down, give me a 1. I multiply 1 by 2 and I get a 2. Add that to 0 and I get a 2. Multiply that by a 2. So this 2 out here times this 2 gives me a positive 4. 4 minus 1 or -1 plus 4 gives me a positive 3. This 2 times 3 gives me a 6. Add that to the 2 gives me an 8. 8 times 2 is a 16. 16 minus 4, or -4 plus 16 is a positive 12. 12 times 2 becomes 24. 24 plus 9 gives me 33. So when that's all said and done, this division problem, I know when we divide this 5th degree polynomial by x minus 2, I get x to the 4th plus 2x to the 3rd plus 3x to the 2nd power plus 8x to the 1st plus 12, and then plus remainder of 33. Or if we'd rather write it out in the more formal way, I'd say plus 33 over x minus 2. That's the more formal way of writing it. So there we go. That's the division. This would have taken us a lot longer using long division. With synthetic division, it goes through pretty quickly. Again, as long as I know that I have to have that 0 as a placeholder anytime I don't see a term. So we have to step down by degree 1 each time. Let's do one more example using synthetic division. Here I have a cubic polynomial divided by x minus 2. Go ahead and push pause on the video if you want and try it on your own. In a couple of seconds, I will show you how it's done. All right. In this case, what we do is we write a 2 in the box. Again, I call that the box. Some people call it something else, I'm sure. And then my coefficient of x to the third is a 1. My coefficient of x squared is a -9. My coefficient of x is a +9. And my coefficient, well, not my coefficient, but my constant number is a +10. Now we're ready to go through the process. 1 drops down. Then I multiply 1 by 2, and that gives me a +2. When I add those two numbers, I'd get a -7. -7 times a +2 gives me a -14. When I add 9 plus -14, that gives me a -5. -5 times 2 is a -10. And 10 minus 10 gives me a remainder of 0. Now, this remainder of 0 means something. It means that if I divide this cubic polynomial divided by this linear polynomial, I get the quadratic polynomial x squared minus 7x minus 5 with no remainder. That's like adding a 0 over x minus 2. 0 over anything is 0. So with no remainder, that means when I divide these two polynomials, I get out a resulting polynomial, which is a very nice situation. In fact, it's also true, I just want to point out, that this also means that if I multiply both sides of this equation by an x minus 2, what I would get out is an equation that says x to the third minus 9x squared plus 9x plus 10 is equal to the polynomial x minus 2 multiplied by the polynomial x squared minus 7x minus 5. So these two polynomials multiplied times each other give me back my my dividend. So my divisor times my quotient gives me my dividend. And that's an interesting thing. That happens only because I got a 0 as a remainder. Technically, in my previous problem, I could have also said that. I could have said this whole thing multiplied by x minus 2 gives me this x to the fifth polynomial. But this is not a polynomial because I have a remainder. So that 33 divided by x minus 2 told me that's I got not a polynomial there. Whereas this example, obviously I got a polynomial when I divided. So that's a very nice feature to have when we divide, getting no remainder, that is. Now, I want to point out an interesting connection. We had the polynomial x to the fifth minus x to the third plus 2x squared minus 4x plus 9, and we divided it by x minus 2. We also had the polynomial x to the third minus 9x squared plus 9x plus 10, and we divided that by x minus 2 as well. So what would happen if we plugged in 2 into the polynomial function whose output were those polynomials? So in other words, if I had a polynomial function, which was that x to the fifth polynomial, what would happen if I plugged in 2 into that? If I had a polynomial g of x, which was that x to the third polynomial, what would happen if I plugged in 2 into that? Go ahead and do the computation if you'd like. If you want to do it on your own, push pause. I'm going to do it right now, though. So f of 2 in this situation would give me 2 raised to the fifth power minus 2 raised to the third power. That's minus, and then 2 is being raised to the third power, plus 2 times 2 squared minus 4 times 2 plus 9. I computed that on my calculator, and I ended up with 33. When I plug in 2 to the other polynomial function, I get 2 to the third power minus 9 times 2 squared plus 9 times 2 plus 10. If you plug that into your calculator, you end up with 0. So in both of these cases, we ended up getting our remainder when we plugged in the 2 into the polynomial function. So remember that I got a remainder of 0 using synthetic division when I divided by x minus 2. On the second problem, when we divided by x minus 2, I got a 33 as the remainder when we divided by x minus 2 in the x to the fifth problem there. And so you may say, well, does this only work with 2? Or would this also work with something like a -3? Let's check this out. What if you plugged in -3 into this x to the fourth plus x to the third minus 3x squared plus 4x minus 5 polynomial? Now you have to be pretty careful about this because you're plugging in a -3. So be careful about how you do your parentheses. That parentheses should always be around the negative. When you plug that in, and I just will plug it into my calculator and then compute that, I ended up with a positive 10. You can check that on your own as well. So notice every time we're dividing by this x minus r number, the remainder that we get is the exact same number as what we get by plugging in that r into the dividend here. And so there's a really nice connection between the remainder when we divide and plugging in the number into our dividend. If I have a polynomial function and I divide it by x minus r, this f of x does have to be a polynomial function, and I end up with the quotient plus a remainder of a, then when I plug in the r into my polynomial function f, I will in fact get an a. Also, the reverse is true. If I were to plug in an r value into the polynomial function and get a, then when I divide that polynomial function by x minus r, my remainder is going to be a. So there's this really nice correspondence between the remainder and the output. Now, if we think about what this is going to imply, a remainder of 0 is going to be equivalent to getting a or finding a 0 of the polynomial function. That's what we're going to use in the next section coming up. But a 0 remainder means that I found a 0 of the polynomial function. And moreover, then I can write it like this, that x to the third function can be written as a product of polynomials of lower degree. And the reverse is also, or the converse is also true. If I do synthetic division and I don't get a remainder of 0, then that r is not going to be a 0 of the function because it's going to have output that's non-zero. And this polynomial, this dividend over this divisor doesn't give me out a polynomial. So I won't be able to write this dividend as a product of my divisor with another polynomial. So I can't do that in this case. But in this case, when I got a 0, I could do that. I could write it that way. And zeros of polynomial functions are going to algebraically show up as when we divide x minus that r, we get a 0 remainder. Let's check out one more example. Let's divide using synthetic division. And from that, let's just decide if -5 or -5 is a 0 of the polynomial function f of x equals x to the fourth minus 3x to the third plus 9x minus 10. Push pause on the video if you'd like to do that on your own. I will do it in a couple of seconds. All right, let's start with the synthetic division. In this upper left-hand box, I'll put a -5 because we have an x plus 5 in the denominator. When I write the coefficients, coefficient of x to the fourth is 1, coefficient of x to the third is a -3, coefficient of x squared is a 0. Be careful on that one. Coefficient of x to the first is a 9, and coefficient, well, or the constant number is a -10. So first step, 1 drops down. 1 drops down becomes 1. 1 times -5 is a -5. -3 plus a -5 gives me a -8. Multiply that times a -5, and I get a positive 40. 40 plus 0 gives me 40. Multiply 40 times a -5. 40 times a -5 is -200. Plus 9 gives me a -191. And then if I multiply that times a -5, I end up getting a 955. That's positive 955, which when I subtract 10, I get a 945, or add a -10, I get that. So what I end up with is that this polynomial is equal to x to the third minus 3x squared. Oh, I'm sorry, minus 8x squared. I saw that. Minus 8x squared plus 40x minus 191 plus a remainder of 945, or you can write plus 945 over x minus 5 if you'd like. And if we had a function, we'll call it f of x, that was x to the fourth minus 3x to the third plus 9x minus 10. If I plugged in a -5 into that function, if I've done all my math correctly, I should get 945. By the way, that's always a good check that I've done my synthetic division correct as well. Just plug in the number into the function, plug in the number into the dividend here, and see that you get the remainder. If you did, then you probably did your synthetic division correctly. If you didn't, then probably something went wrong. I did that and did check on my calculator. Now, once again, that means that this dividend cannot be written as x plus 5 times another polynomial, because we know it's going to be x plus 5 times this thing, and this thing is not a polynomial. On the other hand, if we did get a 0 like we did in the previous problem, then we could say this dividend can be written as the divisor times the quotient. We don't want to always say divisor times quotient. So we say that this polynomial factors into x minus 2 times x squared minus 7x minus 5. Another way to phrase that is that x minus 2 is a factor of this cubic polynomial x to the third minus 9x squared plus 9x plus 10. And we're going to use that term of factor from here and in the next few sections. And really, you'll hear that throughout your mathematical career, I'm sure. But just to restate what's going on, assume we have two polynomial functions. If f of x divided by g of x is a quotient with remainder of 0, then I can rewrite f of x as a product times the quotient and the divisor. So f of x will be q of x times g of x. If that is the case, if we have remainder 0, then we can say that g of x is a factor of f of x. We know from earlier that remainder of 0 means that we have a numerical 0 when g of x looks like x minus r. So when g of x looks like x minus r, remainder of 0 means that when we plug in r into my function f, I've found a 0. So every 0 of the function has x minus r. It means that x minus r is a factor of that function. When you put this and the previous this together. So if a is 0, then that means x minus r is a factor of f of x. So if we have remainder 0, then x minus r is a factor. That means r is a 0 of the function. And that's a really nice place to stop. In the next section, we'll take a deep dive into finding the zeros of polynomial functions. So that's it for polynomial division, at least what we're going to go over in this class. We have two types, the long division and the synthetic division. Synthetic division is a little bit quicker if we have x minus r as our divisor. And that concludes this video.